Okay, on this one, I got a rod, 9 kilograms. Again, when it's horizontal, there's no stretch in the spring. I want to figure out basically the force going on at pin A when I'm at 45 degrees. I know the angular velocity at this point. Okay, the spring is always remaining horizontal. Anyway, let's go ahead and start by drawing our free body diagram here. So we'll start with this. Okay, so here's my free body diagram. Now, the first thing I got, easy thing, is my weight. Whoops. Oh, God. Pardon me. Okay. So I have 9 times 9.8 acting straight down. Okay, that's the easy one. I also now have my spring force acting, and I know that's going to be horizontal, and that's going to be 150 times S. Let's take 2 seconds and figure out what's going on with S here. So what I have here is a triangle that looks something like this, right? So when that guy is up, right, the whole distance from here to here is 0.8 meters. Okay, and that is when there is no stretch in the spring. Okay, now it swings down and I have this little guy right here, which is going to be 0.8 cosine 45, right? Which means what's left, oh my God, what's left is the stretch in the spring right there. So the stretch in the spring, S, becomes 0.8 minus 0.8 cosine of 45. And that gives me an S of 0.234, which means the force in that spring is 35.15. Okay, so I know the force in the spring now. I have the gravity. Next thing I have is the force at point A. Now, before I get in and draw that, I know I'm going to have, two components, right, for a pin joint. However, I got to think about what direction I'm going to be putting this in so I can draw those A's more effectively. What I recognize here is I've got pure rotation. Basically, and I'm looking for the acceleration of the center of gravity. Again, that's going to be basically making a circle as it rotates around. So for that reason, what I'm going to do is I'm going to set up my normal and tangential axes, meaning I'm going to have tangential in this direction, my normal axis in that direction. So I'm going to set up my pin directions as my normal and tangential, like so. And again, that's because I'm in pure rotation here. So I don't want to set up my X, Y. I always want to set up my axes based on how the acceleration is moving. Now that I've got that, I can go ahead and start summing my forces in those directions. So my forces in my tangential directions are going to be that tangential component of my A vector. Then I've got my gravity, which is acting in the positive direction, cosine 45. So that's going to be 88.2 cosine 45. Again, that is the gravity. And then I'm going to have my spring, which is going to actually be in the negative tangential direction of 35.15 cosine 45. So those are all the forces in the tangential direction. Now I have to talk about the the acceleration in the tangential direction. Now, that is, again, r times alpha, right? Where r is at the midpoint, right? So again, basically I've got alpha r in this direction, and I've got omega squared, or r omega squared, in that direction, right? So in the tangential direction, then again, that's going to be mass times that acceleration, which is 0.4, which is half of the 0.8 times alpha. That's what the linear acceleration in the tangential direction is. Okay, now moving on to the normal direction. Okay, I have the normal component of A. Okay, then my acceleration, or I'm sorry, my gravity is actually in the negative n direction, so that's going to be 88.2 cosine 45. Note that sine and cosine of 45 are the same, so I'm being kind of sloppy with it, not worrying about which is which. And then I have the spring force, which is also in the negative normal direction, which would be 35.15 cosine 45. Now this is going to equal the mass times the acceleration in the normal direction. So again, it's going to be n, and now my acceleration is r omega squared. Again, it gives me omega squared, so that's going to be 0.4 for r, and then omega is 6 squared. And again, that's going to be in the normal direction. So again, setting up your axes based on the acceleration makes the right side of the equation very, very simple. Okay, now I need to do a moment equation. Now here's the thing. I can do two choices, remember, with summing the moments. I can either sum the moments about g, or I can sum the moments about the point of pure rotation, which is something I have here. So we'll sum the moments about point A here. Okay, so the moments about point A, I'm going to have the gravity, and that's going to be creating a negative moment. So 88.2 times the distance, which is 0.4 cosine 45. I also have the spring force. That one's actually creating a positive moment, so it's going to be plus 35.15 times 0.8 cosine of 45. Okay, and now what that equals is I about point A times the alpha. Okay, and what I know here is that the I about the endpoint of a rod is 1/3 ml squared. So that's 1/3 9 times 0.8 squared. And again, that's going to be times alpha. Now here's the thing. I know alpha is going in the negative direction, right? That's going to be going clockwise as it rotates around. Now, don't confuse that with what I have in the tangential direction. The direction of the tangential acceleration, if I have a clockwise alpha, is going to be in my positive t as I have t defined down and to the left. Okay, so you want to be careful with those negatives. Make sure you know what you're assuming. So here I'm assuming I've got clockwise rotation, which is a negative alpha, which leads to a positive tangential acceleration. Okay, now here's the thing. 3 equations, 3 unknowns. My unknowns are an, at, and then alpha. Those are my only unknowns that I've got here. So through the magic of algebra, I find that alpha, which I didn't really need, but comes out in solving it, so I'll write it down. 2.64. An is 217 newtons, and AT, I actually get to be negative 28.02 newtons. And I'll just leave it like that, right? Those are the forces at A in the normal and tangential direction. So again, the key thing here is, 1, remember to set up your axes based on what you know about acceleration. And then 2, I can sum the moments about not only the center of gravity, but I could also do a point of pure rotation. However, when I do that, make sure you use the moment of inertia about that point when setting it up. I guess the third thing to keep in mind is keep track of your negatives, keep track of what you're assuming about motion, and stick with it as you go through these things.